Hello everyone, my name is Zhong. Now I'm studying in Chongqing University of Posts and Telecommunications. I'm so glad to attend the 16th EAI International Conference on Communications and Networking in China. The title of my paper is 6G mURLLC over self-read maximum MIMO systems in the finite blocklength regime. I will introduce my paper from the following 5 parts. Part 1, Background. Part 2, System Model. Part 3, Problem Formulation. Part 4, Problem Solving. And Part 5, Numerical Results. Firstly, let me introduce the background and the motivation of my paper. At present, countries all over the world have successively started the research of the 6th-generation mobile communication systems. Although it is far from reaching the unified stage of 6G definition, based on the research process of many countries, it can be foreseen that in the future 6G will adopt transformative technologies mainly from the following 3 dimensions: self-read network architecture, terahertz technology, and artificial intelligence. The initial prototype of the self-read network architecture is a distributed antenna system, including coordinated multi-point transmission, network MIMO, virtual MIMO, and distributed MIMO. Distributed antenna system is essentially a multi-cell, multi-user MIMO system. That is, multiple base stations in a cell cooperate through a high-performance backhaul link to simultaneously transmit multiple users. Self-read massive MIMO combines the advantages of distributed antenna system and the centralized massive MIMO. That is, introducing the user-centric idea to reduce the distance between the access points and the users. In recent years, self-read massive MIMO systems have received widespread attention for providing consistent and good service and no-interval handover to all users. In the self-read massive MIMO system, a large number of distributed access points are deployed to serve all users simultaneously under the same time-frequency resources, which effectively shortens the distance between access points and users. This can significantly reduce the path loss and use the favorable propagation brought by a large number of access points to reduce multi-user interference, so that the entire area is covered evenly, and the user experience is greatly improved. In order to support the new service requirements, massive, ultra-reliable, low-latency communications in the 6th-generation mobile communication system, Finite Blocklength information theory has been introduced. Furthermore, self-read massive MIMO has emerged as one of the 6G essential promising technologies. A great quantity of distributed access points jointly serve massive user equipment at the same time-frequency resources, which can significantly improve various quality of service metrics for supporting mURLLC. However, as the number of user equipment grows, the orthogonal pilot resources in the coherent time are insufficient. This leads to serious non- or signal pilot contamination and pilot allocation imbalance. Therefore, we propose an analytical self-remassive MIMO system model and precisely characterize the error probability metric. In particular, we propose a finite Blocklength-based system model, formulate and resolve the error probability minimization problem, given the latency requirement. Simulation results verify the effectiveness of the proposed scheme and show that the error probability can be improved by up to 15% compared with the classic pilot allocation scheme. Part 2. The system model. Take into consideration a self-remassive MIMO system, which consists of one central processing unit, K access points, and M user equipment, as shown in Figure 1. M user equipment are served by K access points at the same time frequency resources. It is assumed that the access points and user equipment are located randomly in a wide area. Assume that each access point has n antennas, while each user equipment has a single antenna. Moreover, all access points are linked to a central processing unit through infinite perfect backhaul links. Furthermore, we assume that the system is operated under time-division duplexing mode, which can permit channel reciprocity to require the downlink channel state information by uplink pilot train. In addition, we regard the number of channel use for uplink pilot train as NP, the number of channel use for downlink data transmission as ND, and the number of channel use for uplink and downlink phase as N. That is, N equals NP plus ND. In the uplink pilot training phase, we adopt the minimum mean squared error estimator, and the channel estimator is derived as equation 5. In the downlink finite block length data transmission phase, the signal-to-noise plus interference ratio from the access points to user equipment M is derived as equation 12. Part 3. The problem formulation. In the finite block length regime, the accurate approximation of the achievable data rate for user equipment M, denoted by Rm, which is measured by bits per channel use, is derived as equation 13. As we can see, Rm is a function of the error probability and the number of channel use for downlink data transmission ND. By equivalent substitution, the equation 13 can be rewritten as the equation 15. Then, Rm is a function of the latency Td and the error probability. In the case where the achievable data rates for all user equipment are given, the error probability is a function of the latency Td and the number of channel use for uplink pilot training NP. Our problem is that find the optimal NP, which can minimize the error probability. Part 4. The problem solving. In order to find the optimal palette length NP, the exhaustive search method is often used. However, the low-complexity golden section search algorithm can be used as an effective solution to quickly converge to the optimal palette length, to reduce computational complexity. The detailed steps of the golden section search algorithm are listed in Algorithm 1. The complexity of the golden section search algorithm is much lower than the complexity of the exhaustive search method. Part 5. The numerical results. Figure 3 demonstrates the trade-off between error probability and latency. We can see from Figure 3 that there is a trade-off between error probability and latency over 6G self-remassive MIMO system in the finite Blocklength regime. Therefore, according to the different requirements of 6G applications for latency and reliability, we should reasonably configure the parameters to meet different application requirements. Furthermore, increasing the transmit power of downlink data transmission can effectively reduce the error probability. The theoretical value and the simulation value of error probability and different palette lengths are shown in Figure 4. As mentioned in the previous analysis, proper palette length can reduce the error probability. It can be seen from Figure 4 that the optimal palette length is 50, which is obtained by the golden section search algorithm. By means of the simulation results, it is found that the theoretical value is consistent with the simulation value. We also find that the optimal palette length determined by the low-complexity golden section search algorithm is consistent with the palette length determined based on the exhaustive search method, which verifies the effectiveness of the golden section search algorithm. Figure 5 plots the achievable data rate with varying numbers of access points for the proposed 6G self-remassive MIMO networks. We can observe from Figure 5 that the achievable data rate increases with the amount of access points. It is shown in Figure 5 that a larger multiplexing order QM can increase the achievable data rate. Figure 5 also shows that the gap between different multiplexing orders increases with the amount of access points, which is because of the channel hardening effect. We can also find that increasing the multiplexing order QM can improve the achievable data rate. Specifically, by increasing the multiplexing order QM from 2 to 4, the achievable data rate is improved by up to 6% and 9.9% respectively. Figure 6 shows the error probability with varying amounts of access points. Obviously, we can find that the error probability decreases as the amount of access points increases. Figure 6 also shows that the palette length NP can make an impact on the error probability, and the proper palette length can significantly reduce the error probability, which makes the pilot optimization problem more necessary. In this paper, we have developed an analytical model and characterized the matrix over 6G cell-free massive MIMO mobile wireless networks in the finite block-length regime. We have derived the SINR for each user equipment and analyzed the error probability performance in the downlink data transmission. Then we have formulated the pilot allocation problem with the goal of minimizing the error probability, which had been solved by the golden section search algorithm. A number of simulations have been conducted to verify and evaluate the proposed cell-free massive MIMO scheme in the finite block-length regime. Our research can effectively meet the requirements for mURLLC in 6G networks, and is of great significance to theoretical research and actual deployment of cell-free massive MIMO systems. That's all, thank you.